So we had started the discussion about the equicontinuous families of functions. Let us recall the definition once again. So we had taken E as a compact metric space, and C of E as usual the space of all continuous functions, continuous real valued functions on E with the supremum metric, and A is subset of C of E, okay, non-empty subset. Okay. Then what we said is A is said to be equicontinuous, if for every epsilon bigger than 0 there exists delta bigger than 0 such that wherever, if you take any 2 points in E, distance between x and y less than delta, this implies mod fx minus fy less than epsilon, and this should happen for every f in A, okay, for every f in A. Okay. So suppose if it is just an arbitrary family, then given epsilon this delta will also depend on the function f, okay, but if you can find a delta which works for all functions, okay, that is called equicontinuous family. Okay. All right. Now what are the obvious examples of an equicontinuous family of functions? One obvious example will be, suppose the family contains just one function, okay, suppose A contains just one function, then it is obviously equicontinuous. Okay. What if it contains two functions? Okay. You can find delta 1 for one function, delta 2 for f2, and take the minimum of the two, okay, and then you can extend, right. So one obvious thing to say is that every finite family is equicontinuous. Okay. So that is an obvious thing. Okay. That is, you can say if A is finite, then A is equicontinuous. Okay. All right. We shall see non-trivial examples of equicontinuous families little later. Okay. But before proceeding that, let us also see one example of a family which is not equicontinuous, right. Okay. Because if every family is equicontinuous, then there is no point in making such a definition, right. So okay, let us take the full C of E. Let us take a particular case. Suppose I take C of 0 to 1. Okay. Oh, that is, I am taking this whole as A. Now what is the meaning of saying that a family is not equicontinuous? I mean, for some epsilon they should fail. Okay. That is, for some epsilon, whatever delta you give, you can find some function such that there are 2 points with distance between x and y less than delta, but mod fx minus fy is big. Okay. Okay. We can actually show this in this case for any epsilon, but let us take epsilon is equal to half. Okay. Epsilon is equal to half. Okay. Then for this we will show that whatever delta you take, you can always find a function and the points x and y such that mod x minus y is less than delta, and but mod fx minus fy is bigger than this. Okay. All right. Instead of giving the actual details, I will just give the geometric idea. Okay. Suppose this is the interval 0 to 1. Okay. All right. Okay. Now suppose any delta is given. Okay. Any delta is given, then you choose any 2 points whose difference is less than delta. So suppose this is a point, let us say this is the point x and this is the point y, and such that the distance, that is mod x minus y, is less than delta, whatever be the delta. Okay. All right. Okay. Now remember, our family contains all continuous functions. Okay. All continuous functions. So can I construct a continuous function which is, let us say, 0 at x and 1 at y? That can be done always, right. For example, I can take this 1 here, okay, and 0 here, so this part is continuous, and remaining in y to 1 and 0 to x, what values it takes, I do not care. So I will make it 0 from 0 to x, and I will take something like this from y to 1. This is a continuous function, right, and whatever is the, okay, and that belongs to this C01, okay. And for this, what can you say about mod of fx minus fy? Fx is 0 and fy is 1, okay. So this is 1, okay, and so that is bigger than half, right, okay. And this you can do for whatever delta is given, okay, this you can do for whatever delta is given, okay, right. And you might think that we have, since I have drawn these pictures and also this has something to do with this space 0 to 1, but that is not the case. You can do this in any metric space, given any metric space and let us say two distinct points, you can always construct a continuous function which is 0 at one point and 1 at the other point. In fact, there is more general thing is true, what is called Urysohn's lemma, that is if you are given two disjoint closed sets, okay, then you can always construct a continuous function which takes the value 0 at one closed set and 1 at the other closed sets, okay. But anyway, that is not very important now. Is it clear that this is not an equicontinuous family? Okay, alright. Now let us see further examples of equicontinuous families and also what has this to do with uniform convergence. The main thing is that if a sequence is uniformly convergent, then that set of functions forms an equicontinuous family, okay. So that is the first thing that we shall say, okay. Suppose Fn and F, they belong to C of E and Fn converges to F uniformly. Then suppose you just take this set Fn, n belonging to n, okay. So our set is A is Fn, n belonging to n is equicontinuous. Okay. All right. Let me begin the proof here. Okay. Remember, because of this observation, if you take any finite number of functions, that will always form an equicontinuous family. So suppose there is some equicontinuous family, and if you add some finite number of functions to that family, it will still remain equicontinuous. Or even if you remove a finite number of functions from that family, it will also remain equicontinuous. Of course, removing will never cause a problem, because if this works for every f in A, it will work for any subset of. So once A is equicontinuous, all its subsets will be equicontinuous. Okay. All right. So what we have to do, we have to, given epsilon, we have to show that there exists a delta such that all these things happen. So let epsilon be bigger than 0. This is also one of those standard 3 epsilon proofs or epsilon by 3 proofs, okay, where basic idea is to add and subtract a few terms. Okay. All right. Since Fn converges to F uniformly, Fn also satisfies Cauchy criteria, right. Okay. So let us say that there exists n0 in n such that n and m bigger than or equal to n0. This implies that mod fnx minus fmx is less than, I will take epsilon by 3 for every x in E. Okay. Okay. And since this is true for every n and m bigger than or equal to n0, I can take this m is equal to n0 also. That is how we shall be using in the final proof. Okay. Now look at these functions, okay, f1, f2, etc. up to fn0. Okay, suppose I call this as B. Okay. This is an equicontinuous family because it contains only finite number of functions. So this is equicontinuous. So B is equicontinuous. Okay, so therefore hence there exists delta bigger than 0 such that for all x y in E with dxy less than delta, dxy less than delta, we will have for all these functions. So let me call fj of x minus fj of y less than epsilon. Let us take an epsilon by 3, okay, less than epsilon by 3 for, and this should happen for every fj in B. So that means for all fj in B, or you can say for all j from 1 to 0, 1 to n0, that is the same thing. Okay. Now what we want to show is that this is the delta which will work for the whole family A, and for that we shall be using two things. One is this, we already know that it works for this family, this finite number of functions, and we will now show that it works for every f. Okay. So now let f so now let take any fn in A, okay, and xy in E with distance between x and y less than delta, okay, and we consider mod of fn x minus fn y. Okay. See, if n is less than or equal to n0, there is no problem, this is already less than epsilon by 3. Okay. So we will consider only the case when n is bigger than or equal to n0. Okay. So let fn belong to A, and let us say suppose n is bigger than or equal to n0. That is the only case which needs proof, right? Okay. Okay. Then as I said, we shall add and subtract. Okay. We'll take fnx minus, let us say, fn0x. Okay. So we shall write this as fnx minus fn0x. Okay, I'll write this less than or equal to this plus mod fn0x minus fn0y, and then finally plus mod fn0y minus fny. Okay. And now you will see that the proof is more or less over. If you look at fnx minus fn0x, that is less than epsilon by 3 because of this. Okay. I take m as n0 here. Similarly for this last fn0y minus fny, remember the whole point is this inequality is true for every x in E. Okay. And what about the middle term fn0x minus fn0y? That is because fn0 is in this family, and we have already chosen delta for which all this whole works for every fj in B. So each of this is less than epsilon by 3, and so the whole thing is less than epsilon. Okay. Right. Okay. So what we have seen is the relationship between uniform convergence and equicontinuity. Okay. Now the obvious question is, what about the converse? Suppose we take a sequence which is equicontinuous, okay, then does it follow that it converges uniformly? Okay, right? In general it is not true, but suppose we take equicontinuous and bounded, okay, then we can only say that it has a subsequence which converges uniformly. It has a subsequence which converges uniformly, and that is what is called, or that is one version of Arzela-Ascoli theorem, right? So let me repeat again. Suppose the family is bounded and equicontinuous, okay, then it has a uniformly convergent subsequence. Okay, this is given as one possible statement of Arzela-Ascoli theorem. Okay, right? Arzela-Ascoli theorem also has again, since it's being old, it has many statements. Ultimately one can show that all those are equivalent, and also several proofs. Okay. So the proof which I am going to discuss today is from this book. The author is Bela Bolabos. Volobus, and title is linear analysis. This is because the treatment given here is simpler than either Rudin or Siemens, okay, and that you will notice when you proceed with the proof, okay. So it is, we go to this Arzela-Ascoli theorem. This is one theorem which is also quite useful. Only thing is that all its uses, or at least most of the well known uses, are outside real analysis, okay. That is one of the it can be used to show about the existence of solutions of a differential equations, integral equations, etc. Okay. But anyway, you should know this theorem. So let me again recall the statement. Suppose as usual, let us take E as a compact metric space, and take some non-empty family. Suppose contained in C of E is closed and bounded. Closed and bounded. Then what does the theorem says? Then A is compact if and only if A is equicontinuous. Okay. Okay, let us now look at the proof. Now, even before beginning with the proof, let me make a small remark here. Okay, we have already observed in yesterday's class that whenever it is a metric space, saying that metric space is compact, one of the equivalent criteria is that it is complete and totally bounded, right. Okay. Now we already know that C of E is complete, okay, and we have assumed that A is closed. So that means A is complete, right, that means A is complete. So to show that A is compact, all that we need to show is that A is totally bounded, right. So in fact showing this is essentially same as showing that A is totally bounded if and only if A is equicontinuous, right, okay. Alright, let us take this part first. This is relatively easy. Again, both of these proofs have the same idea, okay. You have to have this epsilon by 3 at various places. Okay. Now, so let us take epsilon, start with some epsilon bigger than 0. We want to show that A is equicontinuous, right. We want to show that A is equicontinuous. That means we have to find a delta which satisfies the required things. Okay. Alright. But we know that A is compact, okay, and hence it is totally bounded, and hence it is covered by a finite number of open balls with radius epsilon. Okay, A is covered by a finite number of okay. What is the rotations for open ball? Do you use this B, A, R or U? Okay, this, okay, fine. So okay, so we can say that since A is covered by a finite number of open balls, what is the meaning of that? It means there exists a finite number of functions f1, f2, fn, such that if you take the balls with center at those functions, A is contained in that. Okay, so we can say since A is compact, that is what I am using is totally bounded. Okay, since A is compact, there exists f1, f2, let us say fn in A, such that A is contained in open ball with center at fj, and let us say radius epsilon by 3 and union j going from 1 to n. Okay. Remember our metric is this supremum given by supremum C d infinity, okay. D infinity or norm suffix infinity, okay, metric given by this. And so by this ball what it meant is that all functions such that mod of fjx minus fx less than epsilon by 3 for all x in E, right, all those functions. So, if okay, A is contained in this, okay, all right. Now you look at this family f1 f2, in fact we are doing something similar to what we did there, f1 f2 fn, okay. Suppose I call this family B, okay, then this is an equicontinuous set, this is because it is a finite, it contains only finite number of functions. So B is equicontinuous, okay. So hence there exists delta bigger than 0 such that xy in E and dxy less than delta. This implies for every function in this mod of fx minus fy is less than, again let us take epsilon by 3, okay, such that mod of fjx minus fjy is less than epsilon by 3 for all j equal to 1 to n, that means for every function in this, okay. And now our idea is to show that this same delta works, okay, again using something similar, because what is happening here is that every function in A is close to one of these functions, okay, and these functions all satisfy this, okay. These are the two ideas that we shall use, okay. So now let us consider f in A, xy in E with dxy less than delta, okay. We want to show that mod fx minus fy is less than epsilon, that is our aim, okay, all right. But since f is in A, f is in this union of these balls, okay, so there exists some j such that distance between f and fj is less than epsilon by 3, okay. So there exists, okay, so there exists j in this set 1 to n, or you can say there exists some fj in B, okay, there exists some fj in B such that this norm of f minus fj suffix infinity, this is less than epsilon by 3, okay. And then consider mod fx minus fy, okay, consider mod fx minus fy, then mod fx minus fy, this is less than or equal to, again we are basically adding and subtracting fjx and fjy, okay. So this is less than or equal to mod fx minus fjx plus mod fjx minus fjy and then plus mod fjy minus fy, okay, all right. And again notice that this first term and the last term, that is less than epsilon by 3 because of this, because norm of f minus fj is less than epsilon by 3, okay, because that is a supremum over mod fx minus fjx for all x in E. So this and that is less than epsilon by 3 because of that, okay. What about the middle term? Middle term is mod fjx minus fjy, that is less than epsilon by 3 because fj is one of these functions here and we have chosen delta corresponding to that, okay. So each of this is less than epsilon by 3 for different reasons, but that is okay, fine, okay. So taking a review of this whole thing, you will see what have we done. We started with an epsilon bigger than 0, okay, and we produced a delta such that for every f in A, okay, and xy in E with dxy less than delta, we have showed that mod fx minus fy is less than epsilon, okay. That means that A is equicontinuous, right, okay. Now let us look at the other way, okay, that is, what does it mean? That we assume that A is equicontinuous and we will show that A is compact. Again, as I observed earlier, showing that A is totally bounded is sufficient, okay. So let A be equicontinuous and epsilon be bigger than 0, okay. And what is it that I want to do? I want to show that A is covered by a finite number of balls with radius epsilon, okay, or which is same as saying that there exists a finite number of functions such that A is contained in something like this, A is contained in ball with center at fj and radius epsilon, okay, that is what we want to show, okay. Now to do that we will use this equicontinuity, okay. First of all, let us first say what happens because of equicontinuity, okay. Because of equicontinuity we can say that since A is equicontinuous, there exists delta bigger than 0 such that for all xy in E with distance between x and y less than delta, we have mod fx minus fy less than, okay, I will again take epsilon by 3 because we have to basically do the same thing, add and subtract a few terms, okay, alright. Now once this delta is found, there is one more thing that I want to observe, okay, and that is the following. Till now we have not used that explicitly, but this set E is metric space, E is compact, okay. Since E is compact, E is also covered by a finite number of balls with whatever radius you want, okay. I will take that radius as delta, okay. So E can be covered by a finite number of balls of radius delta, okay. Okay, so what is the meaning of that? It means that there exists some finite number of points. Suppose I call those points as x1, x2, xn, okay, so such that E will be contained in balls with center at those points and radius delta. So we can say that since E is compact, there exists x1, x2, let us say xn in E such that E is contained in ball with center at xj and radius delta and union j going from 1 to n, okay. There are n points in E, okay, and the ball with center at those n points and radius delta covers E completely, okay. Now what I want to do is that I want to consider values of every function at those n points, okay. Suppose I take any f in A and I consider the values of f at x1, x2, xn, each of this is a real number, so you will get a point in Rn, okay, you will get a point in Rn, okay. So what I want to do is I define the map from A to Rn, okay. And what is the map? F goes to f in A, this goes to this n tuple f x1, f x2, f xn, this is in Rn, okay, right. And in order to, since we are referring to such n tuples, I will give some notation. I will call this f hat. So what is f hat? F hat is this n tuple f x1, f x2, f xn, okay. Now the idea is we shall look at the image of A in Rn, okay. But I also want to regard Rn as a metric space, okay. So I should give some metric on Rn, okay, and there also I shall give this suffix infinity metric, okay, okay. So consider the metric space Rn Rn with this norm suffix infinity or okay or d suffix infinity. What is the meaning? That if you take any f hat like this, its norm is maximum of mod fx1, mod fx2 and mod fxn, right, that is for okay. Okay, so suppose I take all such f hats and okay I will give some notation for this. Suppose we call that set as a hat, okay, a hat, this is the set of all f hat for f in A, okay, this is a set of all f hat for f in A, okay. So this is a subset of Rn, okay, this is a subset of Rn, okay. And Rn, as I said, we take Rn with norm suffix infinity, okay, right. So first I want to say that this set A hat, see remember we started with the set A which was closed and bounded, okay. So I want to say that this set A hat is also closed and bounded, okay, this set A hat is also closed and bounded. So once we say that A hat is closed and bounded, since it is in Rn, it will automatically imply that A hat is compact and hence totally bounded, etc. Okay, but let us, but we will go to that little later. Okay, but first of all let us note one thing. Okay, what is the norm of an element f hat here? Norm of f hat or norm f hat suffix infinity, that is nothing but maximum of mod f x1, mod f x2, etc. because there are n such number values at n points, mod f xn. Okay. Is it clear that this is less than or equal to norm? Okay, because this is supreme of mod fx for all x in E, whereas x1 x2 xn is just some subset of E. Okay, so maximum of those n numbers is obviously less than or equal to supremum taken over all. Okay, and which also means that if you take any two functions, then distance between say that d infinity f hat g hat is less than or equal to norm of distance between f and g. Okay. Okay. Now does that show immediately that A hat is bounded? See, what is the meaning of saying that A is bounded? A is bounded means there exists some number m such that d of fg is less than or equal to m for every f and g in A. Okay, right. It will follow immediately from here that if that is the case, for d hat, d distance between f hat and g hat is also less than or equal to that number m. Okay. Okay. Will it also show that A hat is closed? How does one show that any set is closed? Okay, one can take various definitions about the closeness, but one possible thing is that you can take you can consider the sequence. Suppose some point is in the closure of a set, then there exists a sequence of elements in that set which converges to that point. Okay, so suppose I take f suppose f hat is in the closure of A hat. Okay, right, then there will exist a sequence fn hat which converges to that. Okay, and then you show that the limit f hat is also in the same set A hat. Okay, so that is a element thing. Again it will follow from this. Okay, so I shall leave that to you as an exercise. Okay, show that A hat is closed and bounded. Okay, okay. If since A is closed and bounded, A hat is also closed and bounded, and it follows from this relationship between the two matrices. Okay, A hat is closed and bounded. Okay, but A hat is a subset of Rn. Okay, A hat is a subset of Rn, that is a finite dimensional space and hence compact. Okay, in Rn every bounded set is totally bounded and hence compact, closed and bounded and hence compact, and hence compact. Okay, all right. Now it is compact and okay, hence totally bounded. We can say that A hat is also covered by a finite number of open balls, okay, a finite number of open balls with radius again let us say epsilon by 3, okay. What is the meaning of that? It means that there will again exist a finite number of functions such that if you take balls with the centers at say those functions, suppose those functions are f1 hat, f2 hat, etc., okay, then a hat is contained in the balls with center at those functions and radius let us say again epsilon by 3. So we can say that since a hat is totally bounded, a hat is totally bounded, there exists f1 f2 okay, the number, since there we have taken n such thing, that number need not be same as this, so let us say f1 f2 fm in A, either you can say f1 f2 fm in A or f1 hat etc fm hat in A hat, okay, f1 hat fm hat in A hat such that A hat is contained in union j going from 1 to m, union of open balls with center at fj hat and radius epsilon by 3. Okay. But that is not what we want, okay. What we want is that A is totally bounded, okay. So what I want to say now is that you just take these corresponding functions f1 f2 fm and take the ball with radius epsilon, then A is contained in that, okay. So let me first write that as a, I will write that as a claim and we will give the proof later. Claim is this: A is contained in union j going from 1 to m, open balls with center at fj and radius epsilon. Okay. So suppose we prove this claim, okay, what it will mean, that we started with epsilon, okay, and then we showed that for any epsilon A is contained in the finite number of open balls with radius epsilon. That will mean that A is totally bounded and hence compact, okay. So once this claim is proved, the proof of theorem is over. All right. Okay. Now to show this means what, we have to take some, let f be in A, okay. Then we have to show that this f there exists some fj such that norm of f minus fj is less than epsilon, okay. All right. Now what is the obvious point to start with? Consider the corresponding f hat, okay. F hat is in this, okay. So for f hat there exists some j such that norm of f minus fj hat is less than, you start with that j, okay. So we can say that let f be in A, so there exists j in this 1 to m such that norm of f hat minus fj hat suffix infinity, this is less than epsilon by 3, okay. But this is not what we want actually, okay. What we want is norm of f minus f hat, sorry, norm of f minus fj, that should be less than epsilon. What is the meaning of that? It means that if you take any x, then mod fx minus fjx should be less than epsilon. That is what we want to prove, okay. So let us take that, okay. So let x be in E, okay. Okay. All right. Since x is in E, all right, we may have to perhaps modify this argument here, we will come to that. Since x is in E, x is close to one of x is since E is contained in the open union of the open these j open balls, x is close to one of these x's, okay. X is close to, and maybe we have to take that particular x. Let us see later, okay. So we can say that there exists, okay, for the time being I will call it k, there exists k in this 1 2 m etc. such that x belongs to ball with center at xk and radius delta, that is same as saying that dxy, sorry not dxy, dxxk is less than delta. Okay, do you agree with this? Given any point x in E, there will exist some xk, one of these x1 x2 xn, such that distance between x and xk is less than delta, okay, because E is contained in the union of those n open balls. But if distance between x and xk is less than delta, what we know is that for all of these f, for all the, whatever be the function in A, mod of fx minus fxk, that will be less than epsilon by 3, okay. So then mod of fx minus fxk is less than epsilon by 3. Remember, what is important is that in fact this is something I forgot to write here, that is the most important part, okay. Since A is an equicontinuous family, mod fx minus fy is less than epsilon by 3 for every f in A, okay? For every f in A, you will realize the importance of that when we go to this proof, okay, right. Mod fx minus fxk is less than epsilon by 3 for every f in A. In particular, this is true also for fj, that is the important thing, okay. In particular, this is true because fj is also a member, so mod fx minus fxk less than epsilon by 3, and also mod fjx minus fjxk is also less than epsilon by 3, and that is the fact that we shall be using, okay. Alright, now so what we want to say, so now consider mod of fx minus fjx, okay, and we will add and subtract fxk and fj of xk, okay. So this is less than or equal to mod fx minus fxk plus mod fxk minus fj at xk, and then plus mod fj at xk minus fj at x, okay, right. What is to be observed now? Since the distance between x and xk is less than delta, okay, mod of fx minus fxk is less than epsilon by 3 for every f in A, and in particular that applies to fj also, okay, that applies to fj also. So that is why this mod fx minus fxk and this mod fjxk minus fjx, these two terms are less than epsilon by 3, okay, these two terms are less than epsilon by 3, okay. What remains? F of xk minus fj of xk. What about that? F of xk minus fj of xk, that is nothing but one of the value, that is nothing but one of the values of see, f of xk minus f, is it clear that f of xk minus fj of xk, this is less than or equal to what we would have called norm of f hat minus fj hat, right, okay, because what is norm of f hat minus fj hat? That is maximum of mod fx1 minus fjx1 mod fx2 minus fj, that is maximum of those n numbers, maximum of those n numbers, okay, and here you have got only one of those numbers, so it is less than or equal to f hat minus fj hat suffix infinity, and that is less than epsilon by 3 because of this, because a hat is contained in B, or that is because of this, that is mod f hat minus fj hat is less than epsilon by 3, that was our starting point, okay, okay. This mod norm of f hat minus fj hat, that is the maximum of mod fx1 minus fjx1 mod fx2 minus fjx2 etc. of those n numbers, and this is one of those n numbers, okay, alright. So each of this is less than epsilon by 3 plus epsilon by 3 or which is equal to epsilon. Okay. Okay. This proves the claim, and hence the proof of this, okay, because this means that A is totally bounded and hence compact, okay. That is what we wanted to show, that is if A is equicontinuous then A is compact. Is that clear? Okay. As I mentioned in the beginning, the statement as well as proof of this Arzelà-Ascoli theorem, the way in which I have given here, may not be same in every book, okay, because since there are various equivalent statements about the compactness, different books prefer to give their own versions of this theorem, okay. Instead of saying that A is compact, what they will say is that every sequence has a convergent subsequence, okay. And that is what I said in the beginning, that is if it will follow from this that if you take a equicontinuous family and if it is bounded, then it has a uniformly convergent subsequence, okay. Alright. Now before closing, let us just take an example of a see, till now we have seen the examples of the families which were equicontinuous and which were not equicontinuous. Of course, if a sequence is a uniformly convergent sequence, that is the best example of equicontinuous family, best non-trivial example of an equicontinuous family, okay. Let us now take something else, okay. Suppose I define, let us take E as the set 0 to 1, okay, and suppose I take fn of x as x square divided by x square plus x minus n whole square. Zero less than or equal to x less than or equal to, okay, not x minus n, let me say change slightly, okay, 1 minus nx whole square. Okay. Okay, is each fn continuous? Okay, each fn is, that is no problem, okay, alright. Does the sequence fn converge to some function? Take a fixed value of x, does this converge as n tends to infinity to anything? What is that? 0, right. So fn converges to, so fn converges to 0, okay, we can at least say pointwise, okay, okay, fn converges to 0 pointwise, whether it converges uniformly or not, let us pointwise, okay. Does it converge uniformly? Okay. Again, why does it converge uniformly? Okay, let us check. As I said, the best way to check this is compute Mn or sub-estimates of Mn, okay. What is Mn? Mn is supremum of mod fnx minus fx, right, for x is 0 to 1. Okay, out of which fx is 0, right. So we can forget about that, okay. So it is just supremum of mod fnx, okay, alright. But fnx is also each in 0 to 1, this is also a positive number, okay, so we can forget about mod also, okay. So it is nothing but supremum of fnx for x in 0 to 1, okay, alright, okay. Now suppose you take x equal to 1 by n, suppose you take x equal to 1 by n, what happens to fnx? It becomes 1, right, it becomes 1, okay. So I can always say that this is bigger than or equal to 1, do you agree? Mn is bigger than, okay, it may have some value which is okay, but it's not very important as far as deciding uniform convergence. So Mn is bigger than or equal to 1 for all n, okay. So what does it say about the uniform convergence? Okay, so Mn, so it means that since this does not converge to 0, okay, Fn does not converge to 0 uniformly, right, okay. Does it have any uniformly convergent subsequence? Suppose instead of this Fn, suppose I had taken some Fnk, okay, is it clear then also this will be true, but if you take Mnk, that will also be bigger than or equal to 1, okay. So no subsequence of Fn also can converge uniformly, that is clear, okay. So you can say that this sequence Fn does not have any uniformly convergent subsequence. That is clear, okay. So what does it say in terms of equicontinuity then? Since it has no uniform, it is pointwise, but it has no uniformly convergent family, right? It cannot be an equicontinuous family. That follows. But in this case, I would also like the definition. Okay? I will give that to you as an exercise. Okay? Check by not using Arzela, by using Arzelà-Ascoli theorem, it follows that this is not an equicontinuous family. As an exercise, you try to prove without using that. Okay, prove that this Fn n is equal to 1, 2, etc. is not equicontinuous by using only definition, not equicontinuous, okay. And the idea of the proof I have given you already, okay. To show that something is not equicontinuous, again what you have to do, you have to show that for some epsilon there exists no delta, and it is clear from here what epsilon you should take. Again take epsilon is equal to half, and you know that Fnx becomes 1 somewhere, okay, it also becomes 0 somewhere, okay, at x equal to 0, and that is an enough material to show that it is not an equicontinuous family, okay, and we will stop with that for today.